Hi everyone. So in this video, we finalize the discussion of optimization algorithms for training deep learning models by basically having a brief discussion of two very interesting methods. One is called Polyak Averaging and the other is called Supervised PreTraining. And both of them actually, in one way or another, have been introduced even before deep learning. But let's discuss them while keeping in mind the deep learning application, which is the focus of this course. So Polyak averaging refers to having a running average of the parameter updates that are selected by an optimization algorithm, typically stochastic gradient descent or a version of gradient descent. So the idea came from examples like the cliff example that we discussed before, right? So remember what happens in this example is maybe I choose this point, then this point, and then this point, and then I go back and keep looping like this, right? So the intuition for Polyak averaging is basically, what if you're oscillating between different points and the average of these parameters can give you the point that you're looking for, which is the bottom of the valley right here, right? And actually this original Polyak averaging method, which is basically the running average. So you run stochastic gradient descent for 10 iterations. The output of Polyak averaging at the 10th iteration is the average of the parameters from 1 to 10 of stochastic gradient descent, right? So this original one actually has theoretical guarantees and theoretical guarantees on convergence. But the problem is that in deep learning, so these theoretical guarantees apply to any convex optimization problem, but deep learning, you typically have a non-convex problem. And non-convex is similar to saying that you have different regions of the parameter space, right? So here, this is one region, this is one region, this is one region, and so on, right? So having a running average of all parameters since the start of training may be problematic, because some of the parameters, let's say for example I am in this region right here, some of the parameters in this region are not relevant to what I'm doing right now, right? So that's why the modification to Polyak averaging that's applied in deep learning is basically to have an exponentially decaying moving average. And this is has a very similar gist to what momentum is, to how momentum is applying to updating the gradients for deep learning, right? You also have an exponentially decaying moving average. And here the update will basically be theta hat of t, which is the output at the tth iteration corresponding to the Polyak averaging method, equal alpha times theta hat of t minus 1, which is the output of Polyak averaging at t minus 1, plus 1 minus alpha times theta of t, where theta of t is the output of the original stochastic gradient descent in the tth iteration, right? So you end up by you forget the values of the old parameters, right? So one way to think of this, in some way, that it's if momentum is doing an exponentially decaying moving average of the gradient, this is doing an exponentially decaying moving average of the parameters. But remember that in this equation right here, theta of t is an update from theta of t minus 1, not theta hat of t minus 1, right? So you run stochastic gradient descent in parallel, and then the Polyak averaging is a moving average of the output of stochastic gradient descent. Sounds good? The second method or category of methods is what is referred to as supervised pre-training. And the idea, so in general, supervised pre-training refers to first training a simpler model and then using using a simpler task, and then using the simpler model or the model that's used in the simpler task to initialize a more complex model or a model that's used for a more complex task. So this was first introduced for deep learning in this paper right here, Scaling Learning Algorithms Towards AI. And in this paper, they introduced a very simple yet effective strategy, which is basically if you want to have a deep model, then add the layers in a sequential manner. So add them one by one, and every time you add a layer, you train your model, and then you freeze the weights, and then you add one more layer, and then you train only the that next layer, right? So you use the output of the previous iteration or the previous training algorithm that had a slightly shallower network to initialize the next model. Okay, now so there could be variants of this idea, right? So one variant, for example, is instead of adding one layer at a time, maybe you can add groups of layers, right? And another variant is maybe you can use the trained model either to initialize. So let's say I trained a 2-layer network and then I add one more layer. For the first 2 layers, either I use the weights I obtained from the last training process, either I use them to initialize the new model and then retrain the whole model, or I freeze their weight values and then I train only the last layer, right? So pre-training could refer to either you freeze the values of the weights after training, or you use the values of the weights after training to initialize the weights in the new model. Why is this useful? This is useful for many reasons. So remember the problem that we introduced batch normalization to alleviate, which is basically you have simultaneous parameter updates while you compute the gradient while assuming that the parameters in the other layers are not changing. Here, actually, you can freeze the parameters in the other layers, right? So you can avoid this simultaneous parameter updates, right? In every iteration, maybe you can freeze the weights in the other layers, and then you update only one layer, right? So you could imagine many variants of this pre-training idea. Now, another line of thought related to this pre-training method is basically to use it in a transfer learning kind of manner. Transfer learning usually refers to transferring what one model learned to a new model, right? And then using the new model in a more general task. So it's similar to how humans transfer knowledge from one generation to another, right? So there is this paper that introduced an algorithm for building architectures that they call fit nets. And the idea behind fit nets is basically to train first a wide and shallow network. So it's as if I add all the neurons in 1 or 2 layers, right? And then once training stabilizes, you transfer this to a student network, and the student network is deep and thin. So every layer is small, but it has more layers. And what's the intuition behind this? Is that a wide and shallow network will be more exhaustive, right? So you start off, the first generation doesn't know any prior knowledge, so it does more of an exhaustive search for the right solution. And then once it learns a reasonable solution, so remember, this wide and shallow network will have difficulty generalizing, right? It will typically be custom tailored to the data, right? So then to generalize better, depth is very useful in generalization. But then if I start with the deep and thin network, initializing this deep and thin network could be very tricky. And that's why the teacher network can be useful, because it can give me hints on initializing the deeper and thinner network, right? Now, a common strategy that's used whenever such a transfer methodology is using is basically to use the teacher network to give hints on how the hidden layers of the student network should look like. In general, these hints could be very useful, especially with deeper networks, because in deeper networks, initialization can play a great role in how the result should turn out. Sounds good? Thank you.